Um, my name is Justin Littman. I'm one of the software developers on the Rialto team. I'm fairly new to the team. One of the things I admired about DLSS and this team in particular before I joined was that they did these videos talking about their work in very rough ways, very unpolished, but just trying to be very transparent and public about the work they're doing. So now that I'm part of the team, it's time for me to put my money where my mouth is and present on some of the work we've been doing, in this case, on how the data moves through the Rialto system. Just a couple words of background. Rialto is a researcher information system that we are working on in digital library systems and services at Stanford. I'm going to use the term ETL on and off, and that stands for extraction, transformation, and loading. And it's sort of a technical term for a process for doing data transformation and loading into data stores. So I'm going to just give a quick overview of how data passes through the Rialto system from end to end, and then going to circle back and talk about some of it in more detail. And then I'm going to hand it over to my colleague, Justin Coyne, who will be talking about what the data looks like in the web app. And just to be clear and avoid confusion, yes, there are two Justins. It is confusing to have two Justins on one team, but I am the first Justin, and the second Justin will be taking over. So the first part of the end-to-end is what we call the Rialto Combine. This is really the ETL part of, or one of the ETL parts of the data passing through the system. And the first step in that is retrieving the data from a campus or external API. And again, I'll come back to cover this in a little bit more detail in a minute. The second step is transforming that data into SPARQL statements. SPARQL is a language that is used for querying and updating RDF triple stores. And so we then execute those RDF statements against our SPARQL proxy. What our SPARQL proxy do is that stands in front of our Neptune triple store. It's an RDF triple store. It executes a SPARQL against that and then sends SNS update notifications down the pipe. Those SNS notifications are consumed by, they would be consumed, but this is, I cannot seem to move to the next slide. All right, there we go. This, by what we call our transformation lambdas. And those in turn get some data out of the triple store, transform that data, and update our Postgres and Solr derivative data stores. So our Neptune triple store is our primary source of record, and then we create derivative data stores, which in turn are used to drive the Rialto web app. And Justin's going to, again, provide a demonstration of that. So I'm going to step back to the Combine and talk about that. Here at Stanford, we're very lucky that many of our campus information systems support APIs, or application programming interfaces. And that allows our software to extract, to request and extract the data that we need to load into the system. This is in contrast to a lot of other campus information systems where you get data feeds and don't have the ability to request specifically the data you want and get it in a very consumable format. We also query some external APIs. So one that we work with is the Web of Science API for getting publication data. We're using a Ruby library and framework called Traject to transform the data to SPARQL statements. And I'm going to show you what that looks like, because that's really the, because this is really the sort of heart of where the transformation occurs. Okay. What Traject provides is a domain-specific language, or DSL, for performing transformations. And so you can see here, for example, on line, let's choose a more interesting one. Let's choose this one here on line 53. Where we are extracting some data. Let's see, what are we doing? We are let's choose line 63 is a better example, where we are extracting some data from the JSON, which is the structured data we're getting from the API, pulling out a particular field from that, and mapping it to another field, in this case, to a DC terms identifier field. And so we have written various transforms that allow us to take this data from the APIs, transform it into a hash structure from which we can then produce the Sparkle. There's a number of challenges in doing that. The first is that Traject is primarily intended to map from flat things to flat things. Its primary use case is from MARC bibliographic records to Solr indexing records. And in this case, we're trying to do something that doesn't quite fit that. We're trying to go from what often is flat data to hierarchical data, which is how it is modeled in the RDF triple store. And so this is sort of a point that we're working through and hoping to understand how we can most effectively use Traject to do this sort of mapping. The other thing, I'm sorry, that I meant to show you is what some of this source data looks like. This is the organization data that we're working with. You can see it's structured data in JSON. In this case, it's slightly atypical in that this is data about organizations, and when we request it, we actually only get back one document, and that document is hierarchically structured, and it starts all the way at the beginning with Stanford and works its way down to the smallest department or institute or organizational unit on campus. And so this is, like I said, slightly atypical. Typically, we will get a lot of smaller JSON documents. So if we request a researcher profile, we will get back one record for each researcher. So the last thing I wanted to show you was the Sparkle that's produced by this transform. And so this is the second step, and not that it's that interesting to watch code execute, but you can see that what comes out the other side are these Sparkle statements. And there are two primary kinds that come out. We produce delete statements, and we produce insert statements. And the reason we have delete and insert is because it essentially allows us to do an update of our data. We delete some data first, and then we insert new data. So I think that's all I wanted to cover on the ETL side. We're not going to go into the middle steps in any sort of detail, but Justin's going to show how it comes out on the other side when it's displayed in the web app. So I'm going to attempt to stop sharing and turn it over to Justin to do this. Justin, I think you need to grab it yourself.
You got it.
Awesome.
All right, thank you, Justin. I'm showing now our Amazon console screen that shows some of the Lambdas that make up Rialto. Justin creates that Sparkle, and he sends it to this proxy, which we're calling the Sparkle loader. The Sparkle loader parses the Sparkle and gets any of the subjects and makes them into SNS messages, and then sends them to these other two derivative generating Lambdas. This Lambda, when it gets these messages, goes to Neptune and says, tell me the information about this, and transforms them into a format appropriate for Solr. So once it's been ingested, it automatically goes into Solr, and you can see when we go to Solr, we have some data about this object that we can look up. And then we're using Solr to power this web app. So when we click Browse, and just give it a moment, we get a subset of our users are showing up right now. We haven't got a full set imported, but we hope to soon. And we can see that we have users with their names, and in some cases, they have associations to departments, and then through their department to their school and university. We can also do facets, so we can narrow our search by the department they're in. So here's the 675 researchers that we've ingested that belong to the Stanford Linear Accelerator. And we're also able to just run a text search for names. And so when we do that search, we get our one result. That's where we are for right now. If you like this, please like and subscribe to Stanford University Libraries for further updates. Don't forget to support us on Patreon.
Hey, Justin, one quick question. Can you go back to the AWS console for 1 second?
Yeah.
Could you just briefly, so AWS is of course Amazon Web Services, so this code is running in the cloud. Can you just briefly explain what a Lambda is?
A Lambda is Neptune's function as a service. So it's a small component of code that doesn't have a server dedicated to it, and it only becomes active as you call it. So we don't have to maintain a server, and the code's just available for us to call, and we pay for what we use.
Excellent, thank you. All right, thanks.
It's just to clarify, this is Mike.
Yeah.
Lambda's an AWS service, not a Neptune service.
Thank you.
Right, yeah.